Okay, yes, live. So, welcome everyone to this Audio Engineering Society event coming to you from Anglia Ruskin University in Cambridge. Before tonight's event starts, I just have a couple of housekeeping events. First of all, this AES event is open to both members and non-members. If you are not a member, please consider joining. We have lots of high-value resources online, access to networking events, early information about events like this, and it's well worth joining. And secondly, for those of you who are not here tonight, those of you on Zoom, if you have any questions for our speaker, please use the Q&A button at the bottom of the screen and we'll go through the questions after tonight's event. So that's enough for me. Let me just briefly introduce tonight's speaker. Chris Fryer is an engineer, programmer, a businessman, and a electric guitar player. And and tonight he's going to be talking about his development of real-time simulation of guitar effects and amplifiers using something like Spice, I guess. So that's enough for me. Let me hand over to Chris. Thank you.
Thank you, Neil. And I'd like to say thanks to Neil and the AES committee for this invitation to talk tonight. It's a great honour. Yes, if we can start with my first slide. So my name's Chris Fryer. I started Smooth Hound Innovations in 2013. I used to have a proper job before that. My wife and I have been building wireless guitar systems through 2015 to date. And so they're all designed in the UK, they're built in the UK. And over the last 6-7 years now, I've been working on a system to make the best sounding guitar effects unit, because well, I'll talk about the motivation for it. And digital modeling of guitars and amplifiers is not new. It's been going on since the 1980s, since we've had digital systems that can process audio. And they've improved an awful lot over that time, and a lot of people get a lot of pleasure out of using them. Recent moves towards profiling real amplifiers as opposed to bottom-up simulation, which kind of suggests that maybe the bottom-up simulation isn't doing everything that you should be able to do. And the thought really occurred to me is, well, surely if you actually do simulate every single node in the circuit that you're trying to sound like, it should sound the same. So I went about designing a circuit simulator, and I called the system MySpice. I actually stumbled across how Spice worked myself, and thought I'd been very clever, and then realized that's how people have been doing it all along. And we start off by a bit of basic circuit theory. We use Kirchhoff's law to sum currents at every node in the circuit, and formulate the equation for the circuit to find the unknown voltages and currents. All looks very, very simple. We have a system matrix A, which is a matrix of the conductivities between nodes. We've got an unknown vector, a vector of unknown voltages and currents, and we've got any constant currents separately. And solving that for X should give us the voltage and the currents that we want. Things become more difficult, however, when you have nonlinear components in there. So as an example, a diode has a current which the conductivity changes as the voltage across the diode changes. So if you have if it's reverse biased, or if it's got very low voltage across it, it's got no conductivity at all. If it's got significant voltage across it, then it has a high conductivity. So we can't just make a straight A matrix, because we'd have VAK, so we'd have the voltage in that matrix. So we need to go about it a slightly different way. And the solution is to start off with an estimate of the nonlinear control nodes that you're working with, linearize at that estimate, and solve for the linear version of the circuit then, and take the solution to that as your next best estimate and iterate. So to work through a simple example, if we have a resistor driving a diode, we can set up the circuit equations quite simply. IV in plus ID1 obviously equals 0. The current in the diode is also equal to IV in, and the diode current we have it there, and again the exponential diode current. If we want to solve that at say V in equals 1, we can draw the curve on the left there, which is that equation, which is the system equation, and find where it intercepts 0, which is, okay, that's the intercept point there. So if we start off with an estimate of say 0.3 volts, then we can make our linearized circuit by using the gradient at VAK is 0.3 volts, and the intercept, which is way down there, but find where it intercepts the intercept 0, and then that becomes our next estimate. And we then do the same thing again. We get the new gradient, and we iterate around that. Effectively, we're doing implementing the Newton-Raphson method to find the intercept of a nonlinear curve in this way. But I want to show you this actually happening in practice. This is my software system, and we start off with some schematic capture, which produces a netlist. The netlist is then consumed by MySpice. So MySpice is a Python program which I've written, which produces a solution. The solution then can be turned into C code or Python code, which is what I'll be using to demonstrate some of it. So it really is netlist straight to compiled code. So hopefully let's make that a little bit bigger. Might be easier. And also I want to open up LT Spice, where I've entered my first circuit. So I've entered the circuit with my 10K resistor, my diode, and there's a diode model of a germanium diode, and one in 34A. That then gives us the netlist, which I can look at by saying, so we have a netlist, which is the input voltage, V in, which is going to be a sine wave in this case, the diode. Hopefully it's fairly self-explanatory. And if we ask LT Spice what this looks like, we'll see that we've got 0 volts here, and it's clipping at around 0.2 volts. So if I go back to my simulation code, I can now pull up the Python version of the solver. Set a V into 1.0, which you want. Do some prep, set my initial estimate. I knew this was brave. I've imported the wrong circuit, excuse me. While we're here, I've just run the MySpice function again, so you can see it's reported here the matrix, it's reported the X vector and the B constant currents there, and it's finished up making a Python circuit. So we'll go back and have another go. And for this time, I will have a VAK, good. And I can perform some iterations and print the resultant V. So we started at 0.3 and then 0.26. And now we've converged. So just over 0.2 volts. So this is the Python version of the solver, just at one point showing its convergence. I'll talk a little bit now about some other components that we use in the model, or we can model. So the transistor is an NPN transistor or PNP transistor is a full Abels-Moll BJT model. So that means that it works. It shows all the different states of the transistor. So transistor can be off, transistor can be on in its relatively linear mode, or it can be saturation. It can be in reverse. So this where circuits reverse bias the transistor, it will show that as well. And at each of the, whenever we make a new estimate of the voltages on this, then we can make our linearized version of it. So in this case, we've got the conductor current is a function of VBE and VBC with the derivations that you see there. For valves, there isn't a standard way of modeling valves. We have, excuse me, we have lots of data though. And so what I've done here is come up with some functions that we can fit to the data. The requirement for these functions is that they are differentiable and they want to fit to the data. So they need to be continuously differentiable because wherever we are in the circuit system, we need to be able to find a gradient. And then I've taken points from the data sheets and fitted my curves to them. So now this is a triode. There's one feature probably reasonably noteworthy there. The idea of V effective for a triode. Sorry if I'm teaching people how to suck eggs here, but because your gate is normally below 0 and your anode is above 0, it has a positive voltage on it, then both of those affect how the electrons are drawn up through the triode. So you have this idea of a V effective for the triode such that gate goes up and down, or the anode goes up and down, we get an increase in current. There's another feature, however, that you won't get any current unless you have a positive anode voltage. It doesn't matter how high your gate voltage is, unless your anode voltage is positive, you won't get any anode current. So that's why we need a second function there, J of VAK. So K effective is normally how much current is being pulled through, and the J term is the AK actually getting the electrons to the anode. For the gate current, it's 0 if the gate is negative. We'll go into some more interesting stuff with the pentodes in a short while, but that has a fairly similar effect. As gate goes positive, you start to get current drawn into the gate. And this shows the factors that I was talking about. So as V gate goes up at a constant anode voltage, rubbish, you get increasing current, but also as VAK goes up, you get increasing current. So that's the V effective. And then we've got this feature here, which is bringing in, as VAK comes very close to 0, we get a reduction in current that gets cut off. So you don't get current if you have a negative anode voltage. So similarly for pentodes, when you're researching this stuff, you get these fabulous old data sheets from the 1950s of General Electric's pentodes, and this one's one of the better ones, the 6v6 GT data sheet, because it's got very useful stuff about, we have our, see with the pentode, the screen voltage actually shields the current from the anode voltage, so it becomes much less dependent on anode voltage. That's why these curves are flattening off. But that does result in screen current. which are the dotted lines here, that can go significant, especially in saturation. So having these features in the model is quite important. You know, you might think, oh, I don't even need to worry about the screen current, it just sits there at 250 volts, everything will be fine. But actually, as you start to saturate it, you can get significant currents in there, and you typically have a kilo ohm or so in a screen resistor in there. And so if you're getting screen currents of 30 or 40 milliamps in a kilo ohm, then you are going to get some dip of your screen voltage, which is a secondary or second order effect on the throughput. We also, on this data sheet, again, it's not common, not very common to have this, but we have data at positive grid voltages. So the plate current here is extended for positive grid voltages 0 upwards, and at the same time we then start to see some grid current. This is EC1 in here, and we start to see some grid current, especially as the anode voltage, again in saturation, you'll start to see that. And much like with the triode, we can take data points off these data sheets and fit some continuously differentiable lines to them to use as our model. So at every point when we're trying to solve our nonlinear circuit, we can differentiate to get the gradients with respect to VG1, VG2, and VAK. So that's the basics of what we're trying to do. We make a matrix, we linearize it at each point, and we converge, hopefully converge to the solution. I've looked at it times, multiple ways of doing it, but it's obviously advantageous, or can be very advantageous, if you start with a pre-estimate from your previous sample, because at a lot of the time you won't have to go very far, but you can get these. I've spent a lot of time in stuck states, particularly with tightly coupled circuits like the fuzz phase. So I was just going to take a few minutes then to show what happens with the convergence. This one I want to use my fuzz phase circuit. So if I touch net/fuzzface.net, I'll make it build that somewhat bigger matrix this time, 14 or 13 by 13, with the unknowns now are things like VEB, Q1, and VCB, and for Q1 and Q2. Now, if I go back to Python, I can import fuzz face. I want to import my helper function called converge. And I want to plot my convergence, which is a function here called convplot. Pass it my solution, tell it the nodes I'm interested in. CEB want to be Q1, Q2, CEB Q2. And if that's all I pass it, it'll use noise. I think it's probably plot conv, not convplot. Takes a little while, but now throws open some graphs. We don't need that one. This is the output, so 1 volt peak white noise going in, making some pretty horrible noises, I'm sure. And this is the convergence. This is just a figure 1 is a log plot of the same convergence. More interesting is the convergence of the various control nodes that we've been asking it to calculate. And you can see in here that as we throw white noise into it, quite high level white noise, these are the convergence steps out to a potential 20 iterations. VB on this one's going positive and negative. The CB is going up to 0.6 volts, which is pretty heavily saturated. But you can see in some places it overshoots, it comes back, but most of the time it is getting there within the 20, well, it is all every time getting there within the 20 iterations we've given it. If I pass it something else, if I pass it a sine wave, clear as to what our sample rate might be there. And we should see that it converges significantly quicker because we're passing a sine wave and we're using the previous solution for each next one. It's taking a lot less time, it's getting a lot less confused. And so that's, yeah, that's convergence. Okay, so a little bit about how we go about the creating the solution. We use a process of Gaussian elimination. So it's also the same process you use for solving simultaneous equations. You basically eliminate your unknowns one by one until you've only got one left. When you've got a 40 by 40 matrix, however, there's quite a lot of different ways of doing that. And so a lot of the work here has been trying to find a way of making a single solution that works across all states. So it is complicated by the fact that if you're doing it by hand, you'd recognize the fact that you've got large numbers that you can combine quite happily, but the numbers in here, the conductances particularly, can range over orders of magnitude. So what you then start running into is you run out of precision. And you say, well, why isn't it doing it? It's doing the right thing, it's producing the wrong number. And the reason is it's run out of precision. And so you quickly realize that you can't do it with floats at all. You need double floats. You need 64-bit floats in order to do this. Then you find that by making different decisions and using different techniques to choose the elimination order, you can significantly affect the end result with that precision. And so we finish up testing it as a Python module called decimal, which starts off with 24 decimal places, which is enormous amounts of precision. And you can use that to check whether your solution has lost significant amounts of data or not. So then how quickly should it go? Well, these are theoretical numbers, and by doing it with the method we do, we come down quite a long way from this. But remember, your matrix changes every convergence step. And so you effectively need to invert the matrix up to 20 times per sample, and you're doing that 48,000 times per second. And a typical valve power amp might have 40 nodes in it. These are big matrices. And so to do all of that would require 50 billion double precision floats, and I want to do it on a platform, which I'll talk about in a short while, which can manage a couple of gigaflops per core. So we need to we need to make sure we're doing it efficiently. I'll come on to that in a second. Let's just see how we've got on with that then. If I go back to LT Spice and open recent, the fuzz-based one we've been talking about. There's these other ones. And this is set to simulate 20 seconds worth. Let's simulate that. And see down here that it's simulating away. And it says at the bottom here that the simulation speed is 1.6 seconds per second. So LT Spice is doing a good job of it, but even doing 2 transistors, it's only just managing it on a pretty powerful laptop. If I look at my compile code, I can test my C code for the fuzz-based circuit and ask it to do 20 seconds of it. And it's done it in half a second. So it's doing 35 times real time. So now we're into a region that we can definitely do that in a relatively small core. I can zoom in on that and just give some idea. I'm not doing a sample by sample comparison, but that's the solution that my simulations come up with. And if I zoom in on the Spice one, you should see something hopefully pretty similar. This. So yes, that's a demonstration how fast it'll go. I'll get that in a second. Let's just close this. There are other things that we need to do in order to achieve simulating full amplifiers, however. There's some things you can do by understanding how the circuit works. If you've got a valve driver and you know by design that it can't overdrive the following valve, then you don't really need to include that gate in that part of the simulation. You can use something passive. You probably just add the capacitance of the following stage. So there's pragmatic things you can do to break things down. And if we look at a circuit like this is the Marshall 1987 Plexi, a 50-watt Plexi circuit, and how we go about breaking that down into simulatable chunks. As I said just now, I happen to know that this driver here, this is a cathode follower. I happen to know that you can't overdrive that gate, so there's no need to include that one. So we have a pre part of the circuit, which is simulated in one block. We have a mid part of the circuit, which includes the tone stack and includes the phase splitter here, because this cathode follower can overdrive the gates of this phase splitter. So if we want this part of the circuit to be simulated correctly, we need that part included in this simulation. And then we have to, for the power amplifier, we have to solve this entire part, but we don't need to include these parts because they can't significantly affect what the way that this behaves. So there's these pragmatic compromises really that you have to go through in order to get something that can simulate the whole. But I claim that it simulates every node. It really does simulate every single node when I run these things. So the last slide is a little discussion about what's now a technology demonstrator, the SIVA system. It's got a lot of ARM cores in it and a stray 8051 in there. So the UI is based around a Cortex A7 32-bit processor running Linux that handles all of your digital I/O, the LCD, expression pedals. It's got an 8051, as they crept in, that just handles buttons and turns that into an I2C interface. The main audio subsystem is around a Cortex M4. So that takes samples from the ADC or samples from a wireless system, passes them over SPI to the number cruncher, which is a quad-core A53, which is a 64-bit processor running 1.2 gigahertz, and that's running bare metal. So that has 100% of its time devoted to simulating things, and it flies. Other systems use TMS DSP systems. This is much faster. This can do lots and lots of doubles for not very much money. So that's why I chose it. And then those samples results are passed back for play out on the DAC or for recording. They come over to the Cortex A7. So that concludes my discussion. I'm very happy to entertain questions.
Thank you, Chris. That was a really good, interesting talk. Brought back some memories of undergrad maths. I got a few shakes there.
I had to work it out a few times.
Yeah, Gaussian elimination, shock shower. We've got a few questions online I can ask, but first of all, do we have any questions from the room? Not right now. Okay, let me just. Okay, so for the Gaussian elimination, do you use any pivoting techniques?
Yeah, well, you see, you're talking about the undergrad maths again, and I studied engineering here, having completely skipped matrices at school in 1986. I never really got them, to be honest. So when we talk about pivoting techniques, I can't even remember what they are. But we have to rescale, so we do make sure that we don't run out of numbers, but at the same time we want to avoid divisions, because divisions are horrendously slow. So you can get a high precision division can take 10 or 20 times as long as a multiplication can. So when you typically eliminate something in a Gaussian elimination process, you finish up dividing a lot of the time, and so we don't do that. To avoid that, but pivoting, yeah, probably.
What about iterative matrix solutions?
Could they elaborate on iterative matrix solutions?
Okay, fine. Okay, something a bit more interesting. From Jamie, how do you simulate the speaker on the cabinets? You've talked about the amplifiers, the electronic circuits in your MySpice. What about the physicality of the speaker on the cabinet?
Okay, so cabinets, they're pretty linear. Cabinets are. You can overdrive them to the point they'll add distortion. I don't think that tends to sound very nice. So I don't do any non-linear cabinet simulation. What I have done is I have taken all of the speaker manufacturers publish very detailed frequency responses of their guitar speakers, because they're very peaky. Their music doesn't sound very good through them. And so I have developed some code that fits multiple resonant frequencies to that, so you can get a very tight frequency tracking. Most people use IRs for this purpose, which are impulse response filters. I've got an alternate way of doing it, which I use, but no, I don't do any modeling of non-linearity in speakers.
Okay. Have you? Yes. So you've talked about resistors, the capacitors, and the valves. What about transformers?
Again, yeah, I don't do any nonlinear transformer analysis. So they are perfect, my transformers in my simulations. Whether that's reasonable or not, I get to the point where listening to a plexi cascading through and think, I like this, and I haven't gone on to add more distortion from transformers. So it's thought of considered, might well be, somebody could correct me maybe, that saturation in transformers is a real effect. I know it's a real effect. Is it a desirable effect? Does it sound nice? I couldn't say. And no, I haven't done anything about it.
It can have some of the old Fenders used quite undersized output transformers.
Okay.
That lost bandwidth as they started to saturate,
right?
Which had an effect of imparting a different tonality to the tone on overdrive than when it was running clean.
Okay.
Which could be seen as an advantage.
Right. So the same principles could be applied. I've got a bit of hysteresis in a transformer, I imagine. I'd have to think hard about how to add hysteresis into this. Yeah, okay. Well, that should be, yeah. So something for the future, maybe.
Okay, so another question, changing tack slightly. In your system diagram, you've got 4 beefy cores grinding away at the numbers, raw code running on bare metal. And from what we can understand, you're running at 48 kilohertz
Mhm.
sample. How much room would you have for, say, oversampling at, say, 4 times that?
Well, you said they're beefy cores, they're A53s, so actually in a big little system, they're the littles. They're the low power ones. So moving forward, there's plenty of scope, and only going to 1.2 gigahertz as well.
Mm.
So for something that wanted to run 96 kilohertz, for instance, and you could do it now. You just this system can currently do 2 amps at once. So we could run it at 96 kilohertz and do 1 amp. It wouldn't go up by the square. No, it wouldn't go up by the square. It's just doubling the number of samples. So we could do it now if it was needed. And say they were A53s were pokey. I'm trying to think which iPhone it was, but they're not pokey anymore. They're relatively low power, and you can. So if you want to spend more on a processor, you can get comfortably get 4 times the throughput.
Any more questions from the room? No, not yet.
So I mean, just one that you sort of have talked about, the fact that if you've got a continuous wave going through the system, then you can approximate based on the previous sample quite easily because it's quite similar. But with noisy signals, if you've got any kind of noise riding on the signal, you could end up in a situation where you've got quite a high level of noise. Does that cause any troubles with the system?
No, it doesn't. I clearly didn't make that very clear. So I'd say a lot of this is about average throughput. Okay, so you will expect to have large transients a lot. Okay, when you hit a guitar string, 48 kilohertz sounds like high bandwidth. It actually changes quite a lot in one sample. So we have to be able to handle that, but we don't have to do it all the time. So one of the ways I've designed that processing thing is it's got a few samples buffer on it, not very much. But if you say 8 samples buffer, that's not very long. But that means that one sample can take quite a long time if it needs to. And so one sample can require you to, as long as you have time to catch up. So to a great extent, it's the average throughput that matters, which is why I make the point about normally they don't change very much, but you do have to cope. You're right. You do have to cope with big changes, and it does. Yeah.
Okay, so when your circuit distorts, that likely to cause aliasing because you're exceeding nyquist. How do you cope with that?
Well, there's everything will alias. It doesn't matter how high a frequency you put it, you will get aliasing. The question is whether it's audible, and that's the key thing. And I was very worried about it in the initial, but the initial simulations came out, and I've got various tests. If you do a pinch harmonic and bend it, if you ever hear the frequency moving in the wrong direction, that's aliasing. Okay, so that's you detecting that there was aliasing, and I didn't get any, and so I worried less about it. If you do an FFT of it, you can see alias frequencies. Sure you can, especially if you're doing something like a fuzz face, which is all over the place, loads and loads of energy in it. But I can't hear any. Okay, and so there's a few ways you can think about this actually. As to, are you hearing aliasing? You can play it for a long time, with these high frequencies in it. If you're hearing aliasing, you will get a headache. It won't sound nice. Okay, and this does. I've got an AC30 simulation where if you it's got a cut control on the AC30, which puts a capacitor across the phase splitter, if I'm remembering correctly. And it takes out all of the nasties, because the way the preamp's designed an AC30 can generate a lot of nasties, some really high frequency nasties. But everybody plays it with a cut full open. The nasties are nice, if you get what I mean. So there's just, they're there, but if they're in the presence of things which are significantly louder, you won't hear them. So yes, there is aliasing in there. It's at a level that's low enough that I can't hear it. I've not had nobody say they can hear it either. And it certainly doesn't give you a headache. You can play it for hours, and I do play it for hours on end. Yeah. So aliasing is real, but if it's at a low enough level that you can't hear it, it's not a problem.
Point of oversampling, I've just been thinking about it. Since the speaker has about a 4 kilohertz bandwidth, you effectively are oversampling by sampling at 48 kilohertz.
Yeah, trouble with aliasing though is you bounced it back into that band. So you only want to hear this 4 kilohertz out of the 48 out here. When it A-lists, however, it comes back in here, and you can't get rid of it. There is no solution. You can't filter it out. But there's another feature actually, which I think is why one of the reasons why, and I think, I don't know this for sure, one of the reasons why this system's effective is that aliasing comes about from or rather, aliasing becomes a problem by high frequency changes or step changes. To a great extent, this is simulating audio circuits. And so those audio circuits have capacitors in them, and they're simulated in here such that they don't have those large changes a lot of the time. So with the exception of the fuzz face, which obviously wasn't designed by an audio engineer, it's a horrendous circuit. But a lot of the time then we are rounding off in, so for instance, if you were to simulate a sine wave, that will not produce any aliasing at all. It's a perfect sine wave because there's nothing outside the Nyquist. If we're by simulating things that are reduced their audio bandwidth in the first place, then you reduce that as a problem.
Okay. Next question from Jamie again. So you've got this quad core A53 grinding away. Looking to the future, have you looked at maybe using GPUs to give you more processing grunt?
I've looked more at, well, I looked recently at AI chips, neural processors, because they're massive, but there's no doubles in them. You can't do floats in them. So
you can do floats.
Can you?
Tiny floats.
Yeah, okay.
So
yeah, I need 64-bit floats.
Yeah.
So I don't know whether I can do that with a GPU either. I've not looked into using GPUs to do 64-bit floats. I don't know. But all of the intensive math is 64-bit floats. If we can come up with a way of accelerating that with some other, I'd be all ears.
Yeah. AI chips, AI maths is much smaller.
Yeah.
More 8-bit floating point.
I had to think about it. Could we combine those into? I don't know how to do it. My maths isn't good enough, to be honest. I don't know how to do it.
I think we're running out of online. Oh no, we've got a few more. Right, yes, here we go. Of all the amplifier circuits that you've put into your system, which is your favorite?
Plexi. I love Jimi Hendrix. He's by far and away the best guitarist for me. And a Plexi with, and I keep going about the fuzz face, the reason for that as well. A Plexi with a fuzz face in front of it is just, it's bliss for me. I can sit there in the evening whilst my wife is watching something very interesting, probably on BBC 4, sort of thing she watches, and I can be pretending to be Jimi Hendrix, and it's fabulous. So yeah, it's the Plexi. I mean, I love the Fender amps. There's a black face simulation in there, which it sounds lovely. But if I could only have one, it would be a Plexi, not the JCM 800. I was going to with the master volume. It just doesn't improve it for me. Yeah, no, Plexi.
Plexi it is.
The wrong answer.
Yeah.
1987 circuit. Called Plexi because of the plexiglass.
Okay, interesting question from M. Chock. How do you characterize the sonic differences between the real thing and your simulations? And have you found over time, as you've become more accustomed to the specific sound of your simulations, do you find you're steering towards one or the other?
I think that's a really interesting question. I confess I've never done it. I take my system to guitar shows all over the country and I let people do it for me. And I've never had somebody say they didn't like them, you know, in many people playing it. I've never done a straight comparison. I think the point about do you become used to it, that's a real problem, which I do worry about. You know, is it that I think this sounds fantastic because I've listened to it so much, my brain has learned this is the way it should sound? It's possible, but as I say, it's all in the having other people listen to it and how they react to it is the key thing for me. And you know, I didn't buy any of the effects that I simulate, and I didn't buy any of the amplifiers that I simulate. I own a JCM 900, and it sounds miles better than that, doesn't it? I'm totally like Marshall. But I didn't buy it because the circuits are available online. And occasionally. No, I don't think there is that very often. If it sounds good, it's almost certainly right. The people that designed all these effects and these amplifiers were very clever, and they've been making them, and people are still using them for decades and decades and decades. And so it's a bit difficult for this to be a bit wrong. You know, you can have a capacitor in the wrong place, or you can have a wrong value. You can make a mistake in your net entry, but it's a bit difficult for it to be slightly wrong. It's either working or it's not, and when it's not, it sounds horrible.
Okay. I think so I think that's almost the end of the online questions. So questions in the room.
Yes. Have you done JFET guitar preamps?
I have simulated JFET effects. I have not simulated a JFET preamp, no. So I can't try and remember which one it is. There's an overdrive that uses a JFET. I can't remember which one it is.
A lot of them. Mechanical.
No. So I have got a JFET model. I didn't go through it in the discussion. No, I didn't. And yes, and it sounded fine. Also use a JFET in. There's a studio compressor that I do a UREI 1176 studio compressor that I've got a simulation of that I rather like, and that uses a JFET in the feedback.
So JFETs are quite pentade-like,
right?
And typically you've got triodes up front, in a guitar amp.
Yeah.
But people have done a lot of work in this.
So this is one of the things that I could see being a fun thing going forwards. Is it's as simple as putting the stuff into LT Spice and simulating it. You know, it's especially with, you know, somebody comes to me with a new overdrive effect. There's just a few diodes and an op amp or whatever. I can do it in minutes. A big amplifier that I need to separate into manageable blocks, that's more work, but it's not a huge amount of work. So where there are people with hot rodded amps and things, that's something that I can simulate quite nicely. When something more niche, like a niche, I don't know, but a JFET input, something we can add reasonably easily.
Okay. Okay, so that seems to be all the questions, both online and in the audience. So for those of who are listening at home, unfortunately, we're not going to be able to do a demonstration on Zoom because Zoom has issues with audio and stuff. But for those who are lucky enough to be here in the room, once we've finished with Zoom, Chris is more than happy to run through some demonstrations of the system that he's built. So I think for the people online, it's our chance to say thank you very much to Chris. Give him a round of applause. Thank you very much for coming along. And it just remains for me to say thank you for coming along, and have a good evening and goodbye.